spirals in the centers of galaxy clusters. And so that is that.
So are you saying that the massiveness of the galaxies is similar to the radius?
The idea here is, before this plot was made, you know, we weren't sure what you were going to get. So then if you made a plot like this and there was just dots uniformly everywhere, it wouldn't really be telling you anything interesting. Similarly, if we made an HR diagram, we wouldn't bother with HR diagrams if stars were just randomly scattered all over it. It wouldn't tell us anything. But the fact that there's a main sequence was a clue that there was something important going on, and we were able to come up with an explanation that stars that are fusing hydrogen in their cores naturally lie along the main sequence in the HR diagram. So here's a plot for galaxies. They're not just randomly distributed all over the diagram. There's two concentrations that are just given the name the blue cloud. It's not that there's a cloud of galaxies in space anywhere. It's kind of a dumb name. It's just the blue cloud, because on the diagram it looks like a cloud of blue dots. And the red sequence because, I don't know, because they needed another name. And they didn't want to call it the red cloud. Don't ask me. But anyway, the point is, notice that the most luminous galaxies are these ones in the red sequence. And in fact, those are giant elliptical galaxies, CD galaxies, central dominant galaxies, at the centers of clusters of galaxies. And that's not too surprising because galaxies often eat one another. And at the centers of many large galaxy clusters are these giant CD, giant elliptical galaxies, central dominant galaxies, which seem to have grown by galactic cannibalism. They ate smaller galaxies and got bigger and bigger and bigger. And the bigger it gets, the better it gets at eating other galaxies. And so these monsters grew by eating smaller galaxies, basically. It was a battle to the end, and you said chicken first.
Yeah, I did.
Yeah.
I almost always stay later than
Yeah, you do.
Just because I feel like I have like stupid questions, I like to ask you if the phone isn't rolling.
Oh, right. Except that they turn out not to be stupid, and you're just worried that they're stupid.
No, I feel like everyone else who comes in here will probably want the same questions.
That's kind of the thing, right? Is that my experience is when somebody thinks a question is stupid, other people are thinking like, I'm glad she asked that.
Yeah, not me.
Right.
Yeah.
Yeah. And usually they turn out not to be stupid, that's what it comes down to. Just like yours, right? That is not a stupid question about Miller.
Well, because I figured they were an explosion of some type, but I
Right,
just...
but no, it's a very specific kind of explosion, and there's nothing intuitive about it, so, yeah. Yep, okay, see you later.
I'm confused on in chapter 18, it has a long question. It says, know the properties of neutron stars, including roughly their masses and size.
Mm-hmm. How massive is a neutron star typically? It's comparable in mass to...
Isn't it like 10 times solar mass?
No, that would be too big. That would be a black hole if something got that massive. A neutron star's maximum mass is probably 2 or 3 times the sun's mass. So in other words, in terms of about how massive they are, they're about as massive as the sun. They're a bit more massive than the sun typically, but about as massive as the sun. Maybe more like 1.5 times the mass of the sun, something like that. But roughly, they're the mass of a star like the sun, roughly speaking. How big are they? A white dwarf is about the size of the Earth, but a neutron star is about the size of a... No, they're much smaller than white dwarfs. So I will put a reminder kind of picture here of something that could never happen, because if a neutron star got this close to Earth, it would eat the Earth and turn it into a thin smear on the surface of the neutron star. But here's a neutron star compared to Chicago. Neutron stars are about the size of a city, in other words. So a neutron star is about 20 kilometers across, whereas a white dwarf is about the size of the Earth. That's why neutron stars are so spectacularly dense, because you pack the mass of an entire star's worth of material into something that's the size of a city, which is why we have this deal where, like a paper clip would have the mass of Mount Everest for a neutron star.
Aren't they super dense?
The neutron stars?
Yeah.
Yeah, they are the densest. They're the densest stuff we know of, is what it comes down to. Because get any more massive and you turn into a black hole. But a black hole is kind of a different thing, because there's probably not a singularity. A black hole's average density can be larger, but it's not something that you can't get to the inside of a black hole even in principle. Whereas in principle you could send something into the center of into the inside of a neutron star. So in terms of stuff that's not in a black hole, it doesn't get any denser than neutron stars. So they're the densest stuff we know of.
And isn't it the neutron degeneracy pressure that keeps it from collapsing?
It is. Neutron degeneracy pressure is what keeps the neutron star from collapsing despite its incredibly powerful gravity. Because neutron degeneracy pressure is very, very stiff, as it were.
It says what are they made of? Isn't it just iron?
No, that's before the collapse. The neutron star is made almost entirely of neutrons. It's a big ball of neutrons. It's got some protons and electrons in it. There's about, I think it's like 8 neutrons to every 1 proton and 1 electron. But it's almost entirely a big ball of neutrons, which essentially have had all the empty space squeezed out from between them. They're basically kind of piled up right next to one another, which is why it's so dense, because it's kind of like, in ordinary matter, like in this room, the electrons are very far away from the nuclei compared to their sizes. Like if the nucleus was a basketball, the electrons would be orbiting tens of miles away. So you and I and everything in this room are almost entirely empty space. But a neutron star, not so, because all the neutrons are piled up right next to one another. So it's like you've squeezed all the empty space out, which is why it's so dense compared to something like Earth or a regular star or whatever.
Isn't the white dwarf limit, like where it says that the white dwarf can't be bigger than 1 solar mass?
1.44 solar masses. If it's more than 1.44 solar masses, electron degeneracy pressure cannot support it. And in principle, so in the core of a massive star that's made of iron, the core of a massive star about to blow up as a supernova is essentially a white dwarf that has iron instead of carbon. It's like an iron white dwarf in the center of the star. And so when that iron white dwarf has enough mass put onto it by the silicon fusing shell surrounding it, then it becomes, it goes over the white dwarf limit and it collapses and forms a neutron star or a black hole. But that can happen with that quote-unquote iron white dwarf. The reason it won't happen with an actual white dwarf that's a stellar remnant is because a white dwarf that's left over by a star like the sun is made of carbon. Carbon can fuse. So instead of turning into a neutron star, what happens is that before it hits the white dwarf limit, the carbon starts fusing, goes out of control, and blows it to shreds. But the iron white dwarf, quote unquote, that is the core of a massive star, iron can't fuse, and so that doesn't happen. It's able to actually collapse to form a neutron star.
And I didn't completely understand the stellar candles.
on the standard candles, yeah. So what I'm gonna turn my phone off so I can start uploading the videos.